Good morning, dear students. Today we shall see polynomial shape functions. In last class we had learned about the shape functions. What is shape function? Shape function is an interpolating function or an approximating function. It is used to interpolate the unknown displacement field with nodal field variables. You can use polynomials as the shape functions. Why? What is the reason? Because handling the polynomials is very easy. The differentiation is easy. Integration is also easy. Therefore, we can use in general the polynomials as the shape functions. Now we shall see the polynomial shape functions in one dimension. Now we shall see the polynomial shape functions in one dimension. For all the one-dimensional problems, we can use one-dimensional polynomials as the shape functions. Now, observe this function. We have a function here, u, of variable x. It is written as alpha 1 plus alpha 2x plus alpha 3x square plus alpha 4x cube and so on so forth. It ends with alpha n plus 1 into x power n. This is a polynomial of order n, right? So this polynomial, if you observe carefully, we have the coefficients alpha 1, alpha 2, alpha 3, alpha 4 and so on so forth. It ends, the final one is alpha n plus 1. These are known as generalized coordinates, right? These coefficients are known as generalized coordinates. Now, you can write this polynomial as u equal to u represent the displacement. You can write in the matrix form as u equal to some matrix G into alpha. Okay? So, what is G? We write G as a row matrix having the elements 1, x, x square, x cube and so on so forth. It ends with x power n. I tell you an example, thereby you can understand easily. For example, I take a polynomial, say u, as say a plus bx. It is a linear polynomial, right? Now where u is the displacement. Now, in matrix form, how you represent this? You can represent like this. This equals to a row matrix having the elements 1 and x into a column matrix having the elements a and b, where a and b are constants, right? So this is the way we also write here. U equals to a matrix G into another matrix alpha. Okay. Now G is a row matrix having the elements 1, x, x square, x cube and so on so forth. It ends with x power n. Now, alpha is a row matrix. Alpha is a column matrix. Like how we write here this column matrix, alpha is a column matrix. Therefore, when you take the transpose of alpha, it becomes a row matrix. So, transpose of alpha equals to a row matrix having the elements alpha 1, alpha 2, alpha 3 and so on so forth. It ends with alpha n plus 1. Okay. Now, if you observe this polynomial of order n, it has how many terms? N plus 1 terms. N plus 1 terms. This is first term. This is second term. This is third term. This is fourth term. Right? the term number is identified by the subscript of this coefficient. If you observe, the subscript of this coefficient is n plus 1, therefore we have n plus 1 terms in this polynomial. When the order of the polynomial is n, right, the number of terms is n plus 1. This is how we have to remember here. This is how we have to remember here. When the order of the polynomial is n, how many terms we get? N plus 1 terms we get. Again, you see this example. What is the order of this polynomial? 1, x to the power of 1. Therefore, how many terms you get? 1 plus 1. 2 terms you get. Therefore, we have 2 terms. Okay. Right. So now, general form of the two-dimensional polynomial. We see here. We have completed the polynomial of order n in one dimension. A polynomial of variable x. Now we shall see polynomial of variables x and y. A polynomial in 2 dimensions, x and y. A general form of two-dimensional polynomial model is, see here carefully. For two-dimensional problems involving elasticity, we observe 2 displacements. They are, say, u and v. I say u is one displacement and v is another displacement. They are the rectangular displacements. Right? Rectangular displacements. For example, I have a plate like this. Several times I told you. Okay? A plate of uniform thickness. This plate is subjected to several loads in the known directions. These are the forces, say F1 and F2, in the known directions. Right? In the known directions, they are applied. If you take a point here in this domain, in which direction it takes place? In which direction the displacement takes place? The displacements occur in 2 directions. Right? I say this is the reference frame. Say OXY. OXY is the reference frame. Now I observe this point. This point displaces in 2 directions. The first displacement may occur in this direction and another displacement may occur in this direction. Right? Okay. Now, the other displacement may occur in this direction, like this. It may occur in this direction. If this is the displacement, say u, and this is the displacement v. They are the perpendicular displacements. Okay, u is a function of variables x and y, and v is also a function of variables x and y. Because it is two-dimensional problem, we observe 2 displacements at each point in the domain. For these displacements, we have to write the polynomials. How? U is a function of variables x and y. We write here. U is a function of variables x and y. How you write? Now, which equals to alpha 1 plus alpha 2x plus alpha 3y plus alpha 4x square plus alpha 5xy plus alpha 6y square plus alpha 7x cube and so on and so forth. And it ends with, say, alpha m yn. Okay. Nextly, v is a function of variables x and y, which equals to alpha m plus 1. Say here, this coefficient is alpha m. The next one we take alpha m plus 1 plus alpha m plus 2 into x plus alpha 3 m plus 3 into y and so on so forth. This is how we write the polynomials for the displacements u and v in terms of variables x and y. right? In matrix form, if you write, how you write? A column matrix having the elements u and v, which equals to a matrix, say G, into another matrix, say alpha. Okay? This matrix G contains the generalized constants appearing in the first expression, first polynomial, and the generalized constants appearing in the second polynomial. Okay? Now, this is a matrix of size 2 by 2 having the elements G1, 0, 0, G1 into alpha, another matrix. Now, what is G1 here? If you observe, G1 appears as a row having the elements 1, x, y, x square, xy, y square, x cube, and so on and so forth. It ends with y to the power of n. And so here alpha. Alpha is a column matrix. Now transpose of alpha is a row matrix. Right? Now it is a row matrix having the elements alpha 1, alpha 2, you get all these. Alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, alpha 6, alpha 7, so on so forth. Alpha m. Next, alpha m plus 1, alpha m plus 2, and so on so forth. It ends with alpha 2m. This is how we write. Right? In two-dimensional problem, the total number of terms m, total number of terms is denoted by, say, m. The total number of terms m in a complete nth degree polynomial is determined according to this formula. This is the formula for determining the total number of terms. M equals to n plus 1 into n plus 2 by 2. What is n here? N is the order of the polynomial. Okay? Order of the polynomial. For first order polynomial, how many terms you get? Put n equal to 1. So 1 plus 1 into 1 plus 2. How many terms you get? When n equals to 1. We see here, n equals to 1. Now m equals to n plus 1, that is 1 plus 1 into n plus 2, that is 1 plus 2 divided by 2. Now 2 by 2 get cancelled, you get 3 terms. m equals to 3 when n equals to 1. Then how you get u? U equals to alpha 1 plus alpha 2x plus alpha 3y. Because the order of the polynomial is 1. Hence you get, when n equals to 1, you get u of variables x and y, which equals to, say, alpha 1 plus alpha 2 into x plus alpha 3 into y. This is how you get. How many terms are there? 3 terms. Similarly, v also you get. How you get v of variables x and y equals to, okay? Now this is alpha 3, therefore you can write here alpha 4 plus alpha 5 into x plus alpha 6 into y. This is how you get. If you take n equals to 2, that we see. When you take n equals to 2, take n equals to 2. Then according to the formula, number of terms m equals to n plus 1 into n plus 2 by 2. n plus 1, that is 2 plus 1 into 2 plus 2 by 2. How many you get? 3 into 4 by 2, and here you get 3 into 2, that is 6. Here order of the polynomial is 2. Therefore, how you write the expression for u? U of variables x and y equals to, now alpha 1 plus alpha 2x plus alpha 3y plus alpha 4x square plus alpha 5xy plus alpha 6y square. Up to this you have to consider. Up to this you have to consider. This is your polynomial for u when the order is 2. Similarly, the polynomial, for v when n equals to 2, how you get? V equals to alpha m plus 1 plus alpha m plus 2 into x plus alpha m plus 3 into y plus alpha m plus 4 into x square plus alpha m plus 5 into xy plus alpha m plus 6 into y square. It ends with alpha m plus 6 into y square. In each polynomial, how many terms will appear? 6 terms when n equals to 2. Okay, now we can also write the polynomials in 3 dimensions. The polynomial in 3 dimensions with order 1. We say first order polynomial. The polynomial in 3 dimensions with order 2. We say second order polynomial. The polynomial in 3 dimensions with order 3. We say third order polynomial. Right? This is how you can also write 3-dimensional polynomials for nth order. When you write the 3-dimensional polynomials here, the coordinate z also comes into consideration. Then, in the problems of elasticity, how many displacements we consider? 3 displacements. The displacement, say u, v and w. All the 3 displacements are the rectangular displacements. If you consider a point in the domain which can displace in 3 perpendicular directions, the 3 displacements are mutually perpendicular to each other. Therefore, u is a function of variables x, y and z, and v is a function of variables x, y and z, and w is a function of variables x, y and z for 3-dimensional polynomials. Okay, now see how you write the polynomial of variables x and y. As I said, you can remember the 2-dimensional polynomials and write for n equal to 1, n equal to 2, n equal to 3 and so on and so forth. The alternate way of remembering the 2-dimensional polynomials is remembering the Pascal Strategy. Anyhow, one can write 1-dimensional polynomials without any difficulty. Because 1-dimensional polynomials contain only one variable x. Writing 2-dimensional polynomials are slightly difficult. Therefore, how you write the 2-dimensional polynomials? You can write remembering a Pascal's triangle. This is a Pascal's triangle which one can remember for writing 2-dimensional polynomials. Observe carefully. When you want a polynomial with only one constant, without the linear term, then take the constant term. Okay? Then you get only one term. The polynomial contains only one term. Okay? When you want the linear terms also, then the polynomial contains 3 terms. When the order is 2, then the polynomial contains 6 terms. We have the formula n plus 1 into n plus 2 by 2 for determining the number of polynomials. for determining the number of polynomials. So what is the formula? The number of, for determining the number of terms, what is the formula? M equals to n plus 1 into n plus 2 by 2. M is the number of terms appearing in the polynomial. Right? I put n equal to 1, then what you get? 2 into 3 by, okay, then you get n plus 1 into n plus 2 by 2. Okay, when n equals to 1, you get how many? Okay, and you get a two-dimensional polynomial of order 1. So how you get when n equals to 1? You get a linear polynomial. Then your polynomial contains the constant term and the linear terms. You get 3 terms. So therefore, how you write u equals to some constant, say a plus b into x plus c into y. You get like this. Another displacement v of variables x and y, v equals to, now b plus e into x plus say f into y. This is how you get. Then you get a linear polynomial. If you want second order polynomial, you say quadratic. When the order is 3, you get cubic. When the order is 4, you get quartic. When the order is 5, you get quintic. Then hexagonal. Okay? These numbers represent the number of terms. If you want a second order polynomial, how you write? Now, I can write the polynomial for the displacement, say u, when order is 2, n equals to 2. How you write? Say a1 plus a2x plus a3y, next plus a4 x square plus a5 xy plus a6 y up to this. Up to this we take all these. Constant term, x term, y term, x square term, xy term and y square. How many terms are there? Total 6 terms. Similarly, for the displacement v, how you write? I write, say b1 plus b2x plus b3y plus b4x square plus b5xy plus b6 y. This is how I. V also contains constant term, x term, y term, x square term, xy term, y square. Okay, next. When the order is 3, you get a cubic polynomial. You get a cubic polynomial. How you get? Say u equals to, now say a1 into 1 plus a2 into x plus a3 into y plus a4 into x square plus a5 into xy plus a6 into y square plus a7 into x cube plus a8 x square y plus a9 xy square plus a10 y cube. Okay, next. Now the displacement v, how you write? Displacement v equals to b1 into 1 plus b2 into x plus b3y plus b4x square plus b5xy plus b6y square plus b7x cube plus b8x square y plus b9 xy square plus b10 y. This is how you can write, the third order polynomials. Okay? When the order is 4, your polynomials will contain, these terms. Understand? So this is how one can remember, the Pascal's triangle for writing two-dimensional polynomials of any order. Okay? Right. Now, this is about the three-dimensional polynomials. A general three-dimensional polynomial shape function of nth order is given like this. As I said, for how many displacements we write? For 3 displacements. U, V and W. For the displacement U, we write the polynomial like this. Alpha 1 for alpha 2x plus alpha 3y plus alpha 4z plus alpha 5x square and so on and so forth. It ends with alpha m into x to the power of n minus 1 into z. Next, v equals to, what is the next term? The next term you write, taking the next generalized coefficient. Okay, now alpha m plus 1 plus alpha m plus 2 into x plus alpha m plus 3 into y plus alpha m plus 4 into z plus alpha m plus 5 into x square and so on and so forth. It ends with alpha 2m into x to the power of n minus 1 into z. Next, w, which equals to the next coefficient, right? Alpha 2m plus 1 plus alpha 2m plus 2 into x plus alpha 2m plus 3 into y plus alpha 2m plus 4 into z plus, and so on so forth. It ends with alpha 3m into x to the power of n minus 1 into z. You can write like this. If you face difficulty in writing, taking alpha 1, alpha 2, alpha 3 and so on, alpha m, you can write like this. Say u equals to, now u equals to, say a1 plus a2x plus a3y plus a4z plus a5x square and so on and so forth. Next, v equals to, say b1 plus b2x plus b3y plus b4z plus b5x square and so on and so forth. Next, w equals to, say c1 plus c2x plus c3y plus c4z and so on and so forth. Like that also you can write anyway. Okay? Now, see here, these 3 equations we can represent in matrix form like this. How we have done for two-dimensional polynomials in matrix. So what is G1? G1 is a row of elements having 1 x, y, z, x square, xy, y square, yz, z square, zx and so on. And alpha is a column matrix. You get transpose of alpha, a row matrix like this. A row matrix like this, containing all the generalized constants. Okay. Now, the number of terms m in nth order polynomial are variables x, y and z. You can determine using this form number of terms appearing three-dimensional polynomial. Number of terms appearing in three-dimensional polynomial you can determine using this form. M equals to n plus 1 into n plus 2 into n plus 3 by 6. Okay. I take n equal to 1, I get a linear polynomial of 3 dimensions. When n equals to 1, m equals to 1 plus 1 into 1 plus 2 into 1 plus 3 by 6, you get 4 terms. You get 4 terms. How you get? You can try. You can try. Let us see. Say u equals to a plus bx plus cy plus dj. Order of this polynomial is 1. It is a linear polynomial of variables x, y and z. How many terms are there? 1, 2, 3 and 4. You have 4 terms. Similarly, V, which V, right? Now, E plus Fx plus Gy plus Hz. You can write like this. Similarly, for W you can write. In each polynomial, 4 terms will enter. When n equals to 2, how many terms the polynomial contains? 10 terms. Writing 3-dimensional polynomials is very difficult. You have to do careful. Now, you can also write 3-dimensional polynomials remembering a tetrahedron. For writing 2-dimensional polynomials, we can use Pascal Strategy. For writing 3-dimensional polynomials, you can use tetrahedron. It appears like this. When you remember this tetrahedron, you can write 3-dimensional polynomials. Okay? When n equals to 1, your polynomial is a linear polynomial, then how many terms do you contain? How many terms the polynomial contains? 4 terms. When n equals to 1, the polynomial is linear polynomial. It is a 3-dimensional polynomial which contains how many terms? 4 terms. When the order of the polynomial is 2, then how many terms it contains? 10. What is the formula? N plus 1 into n plus 2 into n plus 3 by 2. This is the formula. Okay. So therefore, you get 10 terms. Next, when the order of the polynomial is 3, how many terms the polynomial contains? 20 terms. I take n equal to 1, then I write u. U is a function of variables x, y, which equals to, say, a1 into 1, a1 into 1, a1 plus a2 into x plus a3 into y plus a4 into z. This is how I write. a1 into 1 plus a2 into x plus a3 into y plus a4 into z. Next, the displacement v of variables x, y and z. How I write? I take the other coefficients. Or I can take the next coefficient next to a4. a5 I can take. Otherwise, I write so b1, b2, b3. I consider b1, b2, b3 and so on. Now, what I do is I take b1 into 1 plus b2 into x plus b3y plus b4z. It ends with b4z. Similarly for w, of variables x, y and z, it contains how many terms? 4 terms. Now, what is the, first term? The first term does not contain any variable. I write c1 into 1 plus c2x plus c3y plus c4z. This is how I can write 3-dimensional polynomials when order n equals to 1. When order n equals to 2, then we try for u. U equals to a1 into 1 plus a2x plus a3y plus a4z plus a5x square plus a6xy plus a7y square plus a8yz plus a9z square plus a10zx. This is how we write for u. Similarly, for v and w, you can write 3-dimensional polynomials. Okay? Right. Thank you. Thank you very much.